Swayam Prabha. Digital India. Educated India.
So welcome back. Now this is our turn for going through support vector machine. Again here it will be we will be dealing with linear classifier first, and the same as a decision tree, we will be selecting the best classifier among a set of classifiers. So I think we all know what is separating hyperplane. So these things maybe we no need to cover it here again. But we will be learning what is support vector machine classifier. I will be dealing with only the classification task with the support vector machine. And then we will learn what is the margin, what is the intuition behind this tuning parameters, maybe some geometrical information, and how to learn SVM giving a training data. And as per as your request, I will try to cover nonlinear classification with support vector machine and with kernel tricks. So again we have the same data set D. This is a classification task, so we have X the features and we have Y. Here for the support vector machine classifier we will assume this Y is -1 and 1. It is little different from the logistic regression where we have assumed it to be 0, 1 because we were trying to fit one probabilistic distribution there. We thought it is a binary random variable, so 0, 1. Now we are not thinking that, so it is be -1 and 1. And here also we will be learning where linear classifier H maybe is a hyperplane which is defined by W transpose X. Okay, given W, which is the point of X which are on this equation. So the W transpose X plus B equal to 0 is a definition of a hyperplane. And where is the W here? So this W is actually perpendicular to this hyperplane. This is a W is a vector and which is a directions which gives the direction which is perpendicular to this hyperplane. All the x's which are on this, if you have some x here and if you take the inner product of this x with the W, and then it will give some value and it is a B is a bias. So along with the bias it will be 0. So here we'll call this B as a bias and W is the directions of the separating hyperplane. Now if you think about these two classes, we can have lots of separating hyperplanes, or here for 2-dimensional plots it's a line. And we can have infinite number of W's which can separate these two data sets where they are linearly separable. So first we will deal with the data sets which are linearly separable, so that we have there exists a hyperplane which separate these two data sets. Now which one to choose? Which one is better? So the optimal separating hyperplane can be generated by finding the support point and bisecting them. So maybe it is better I'll go for this like so as we have here some red point and then some blue point, and what is the support points for this data sets. So now you draw a convex hull for each class. So this is the convex hull for this training sample, and this is the convex hull for this training sample. So these are the kind of boundary points of this sample set. And now find out the two closest points, 2 points each from one class, such that the distance between these 2 points is the minimum. So you have to find a point from here and you have to find a point from here. so that the distance between these two will be minimum. So which 2 points are this? Maybe these two are the points. They have the minimum distance, they are coming from both the sets. So these 2 points are called support. These 2 points are support points from each classes. And now you just divide these 2 points in the equal distance, put these 2 points equal distance from your hyperplane, and where the hyperplane will be perpendicular to this connecting line. So if you divide your connecting line here, and your hyperplane will be perpendicular to this connecting line, then this is the optimal hyperplane we want. This is called geometric interpretation of SVM. Now, there are 2 lines you can imagine here, you can draw, which are the support line of these 2 data sets. So we can draw a line parallel to this hyperplane, and that is this. And another line we can draw again parallel to this, and this pass through the support point. So this supporting hyperplanes, these are the supporting hyperplanes. So these are the parallel to the separating hyperplane, and this is passing through the support points. And this distance between these 2 hyperplanes is known as, what is called? Margin. This is called margin. And we want to, when we are learning our support vector using some optimization problem, then we say we want to correctly classify all the points with the margin maximum. Okay. So if this was not the perpendicular to this, but it was somehow equal distance from this point, but it is in this direction, then you can see that this distance was not maximum. So like these 2 points are there. So now this is the W, and you have find some distance here, and now if your line was like this, and then what is the distance between these 2 hyperplane? So these 2 supportive lines, the distance is this one and plus this one. So this one, right? And you can see, if it is not perpendicular, if this line is not perpendicular, then the distance is always decreasing. No? This is now become your distance with this line. So if your line is this, then your distance is this. Right? And when your line was the perpendicular to that connecting line, then your distances was this. You can just use simple trigonometry, these angles and those things, and you can find this will be always less. Then find this hyperplane which is perpendicular to that connecting lines. Okay. So again, so it is our classification rules will be finding one W transpose X plus B, and then with the point X will be finding what is the value, and the sign will be the class level. If it is a negative value, then class is -1. It is a positive value, then class is +1. And the learning means, given the data, we will be learning this hyperplane such that this sign of hyperplane will be equal to the given labels. So that we want g of xi to be yi, that means sine of h of xi to be yi, and that means that yi into h of xi is always a positive quantity. Because if it is a negative and it has a negative sign, negative into negative is a positive. And if it is a positive, it is a positive class, then it is positive into positive is a positive. So we want always this thing to be positive. And then we want, that is why the class, what is the hyperplane, this sum over all the data points to be maximum. So for maximum number of data, it gives some positive value. Now when your data set is linearly separable, then you will be able to find that line where no data set is present. All the data samples, no data sample is on the line. They are away from the line. Whatever is the margin, it's little bit, but it's away. So you can use strict inequality to define your class. Now, we'll first define the loss function we use for SVM. So, for this we know this classification loss function will be either 0 or 1, it should be. No? We have learned it from the logistic regression that classification loss should be either 0 or 1. So, it will be 0 when it is correctly classified, and when it is 1, it is misclassified, then it will be 1. So, when it will be 0, where this quantity is positive, it will be 0, and when this quantity is negative, it should be 1. So, if you draw a 0, 1 classifier, 0, 1 loss, then given a yi and a h of xi, if it is they are less than 0, then it will be 1. So, it will be like this. So, at 0, it will start going 0 this side, and the negative direction this is. This is a non-convex function. So, maybe do you know what is non-convex and what is convex function? Okay. So, the convex function has a similar some kind of like the dome shape function, or if this is a concave, maybe you can say convex function is some pot shape, like nice shape. When if sometimes you have up and sometimes down, and these cases we call it non-convex, and it is hard to solve the optimization problem with the non-convex loss function. So, for SVM, as we solve it with the optimization problem, we found some loss function, we use some other loss function, not 0, 1 loss function. We will use some loss function which is very close to 0, 1 loss function, but it is a convex. So, it has a nice shape, either it is coming down or it is going up. It will not be up, down, it will be not like that. So, first maybe I will talk about this, like in that is why the support vector machine will be having this kind of loss function. So, up to 1, it is greater than 1, it is 0, and if it is a less than 1, then it will be growing. So, it will not be exactly 1. So, it will give some weightage on how badly you are misclassifying 1 point. But for all good right classification, it will give a 0, no weightage for them. So, now we will be formulating it, how we will get that thing. So, as you know that we have said that when the data set is separable, then we will be having the strict inequality for our classification rules. And then when we have it is greater than 0, we should find out some positive number, that is epsilon. It's maybe a little bit bigger than the 0, such that we will use the equality in one side. Is that clear how we can do it? So, when we have something here, then we can just replace this w and the b by this w by epsilon and b by epsilon, and we can say all things, our classifications will depends on the 1. So, that if w transpose xi plus bias is greater than equal to 1, then we will put it as a positive class. If it is less than -1, then we will put it as negative class. So, in support vector method, it is no more it is 0, it will be +1 and -1. Okay. So, So this thing we said that max margin is 2 by norm W, and then we'll be maximizing margin such that all the data points, all the i's, these terms will be greater than 1, and then we can write it will be minimizing this. Maybe we should not have epsilon here. It will be minimizing this such that all the points will be greater than 1. And but what happen if we have non-separable data? So in this case, for the non-separable data, there will be no feasible solution. No W will be finding which will be separable. Then we'll be using the slack variable xi, which allows for that classes to learn overlapping classes. And this slack actually represent the misclassification on the training data. So how much it is away from this plus 1? How much less is from plus 1 is the xi. So if it is not greater than the plus 1, then it must be greater than plus 1 minus xi, when xi is a positive number. And if we take all this misclassification amount, loss, sum over all I, xi, this should be less than t. And this t we want to be small. This is our misclassification error. And this should be small. And t is the tuning parameter here. So that you can use any t depending on how accurate you want your classifier. Accurate on training data, just keep it in mind. If your tree is a very small, then you would like to have a classifier which is very accurate on your training data. That may give you overfitting. So this t parameter you have to decide it. You have to decide with the help of cross validation or some validation. So when t is equal to 0, then we will not tolerate any margin violations, and our margin is then going to be narrower. And when t is little bit larger, then we will tolerate that many of samples to violate the margin, then we will be widening our margin. So if we go back here, so we have this data, and then we have this data, and we know that then we will have this separating hyperplane, and which the margin W is such that this is the margin. So if this is W transpose X plus B equal to 0, this is W transpose X plus B equal to 1, and this is W transpose X plus B equal to minus 1. Then it is actually T then is equal to 0, and then this W, this distance is this much. Now we are allowing 2 misclassification. Then we will be having some other, maybe this one. Maybe in this case, let's change our W a little bit. So in that case, our W will be moving a little bit, maybe this side, depending on the distance between these two. So here the t is equal to 2 and our margin increases. So larger the t will lead the larger margins. And now we can omit that t and we can bring this total whole xi in our objective function. So instead of putting this t value, we can say we will be minimizing the sum of xi when we have some weight with the xi. So now here the lambda is called the trade-off parameter. When lambda is more, like 100 or 1000, then you will be giving more weightage on the misclassification error. Then we will be want to reduce the more the training misclassification, and your margin will be reduced. But when the this lambda is small, that means you are allowing the more misclassification, and this part will get more weightage then for the minimization, and minimization of this part means maximizing your margin. Okay. So there is a trade-off. So whether you will be focus more on minimizing the W norm of W, or you will be more give more focus or weightage on minimizing your classifier misclassification. So for a sample I, this xi I is equal to 0, that means what? When the xi I will be 0, like you solve it, you got a W and you got a B and you got a hyperplane, you got all the xi i's for all i's. Now for a sample I, your xi I is 0, then what is means? So for this point, if we are thinking of this, what is the xi I for this point? So this point, for this point already this W transpose xi plus B is greater than 1. So therefore xi I will be 0. And what will be the xi I for this point? Also it will be xi I equal to 0. Right? It's clear, no? Because here also you will have the minus 1 into some minus number. Here W transpose X plus B is some minus number, so it will be less than 1. It will be again, greater than 1. This will be something less than 0. Right? Now, what will be the value for this one and this one? So you will have some positive xi I because this has deviated from this one line. So this has some xi, this value, right? So this is for this data point, this one yi into W transpose xi plus B is equal to maybe 0.5. So that means we will say this is 1 minus 0.5. It is not 1, no? We can say that it is closer to the hyperplane. So then xi I has some positive value. So for those who are misclassified, will get some positive value in xi I. And what happens when this is on the supporting hyperplane? For on the supporting hyperplane also, the xi I is, so okay, no, on the supporting hyperplane also it is equal to 0, because on the supporting hyperplane it is W transpose xi plus B equal to exactly 1. So your xi I will be 0. Okay. So there is something, another thing. So now think about if you have some black data point here. So in this position, xi i's are greater than 0 but less than 1. In these positions, xi i's are equal to 0. And what happens if your data point just opposite to the classifier? So for this one, it is correctly classified, but it is not beyond the margin. But when it is misclassified, in that place xi I equal to 1. It is greater than 1. So because this on here, on the supporting hyperplane xi I equal to 1, and this is come here, then it will be something like W transpose xi plus B equal to maybe minus 0.5. So then it will be 1 minus 1.5. So xi I will be more than 1.